So we are still, hi everybody, first of all. We are still trying to finalize our calculations of the Bose-Einstein calculation. I will remind you again where we are standing. So we obtained some sort of general expression for the average number of particles, okay, for a system as a temperature. Now, we found that there is a problem with our expression. The problem was that our hypergeometric function f3.2, f3 over 2 of the fugacity had this behavior, okay, as a function of fugacity. Exactly at fugacity equals 1, it was approaching 2 point, what was this number again? 2.61 something, 2. Okay, great. And we had this, and we found out that this imposes some sort of a limit on the average number of particles, but there was no physical limit on the average number of particles, given that it was actually dependent on the temperature. What eventually we found out that when we performed all this integration, okay, so this is n as energetic level, as a function of energetic level, we found out that this guy, okay, was behaving quite smoothly, okay, for all the energetic levels, except what? Except level 0. Okay. Here we had some sort of a delta function. Not exactly delta function, but some sort of a discontinuity of the behavior of the average number of particles per level. And I remind you, this guy n was 1 over e to the power beta epsilon minus mu minus 1. Now, from this behavior we understood, or at least that all our calculations are fine as long as they do not include, okay, as long as they do not include the level, energetic level 0. Why? Because as we approach, we decrease our temperature, and we approach to the lower and lower temperatures specifically to temperature equals to 0. The amount of particles that are sitting in this level are getting so extremely high and so very much distinct from the number of particles that are sitting on the next excited level. So we cannot simply treat this as a very smooth and continuous transition from this point. Okay, so here was epsilon 1, 1, 1, and this guy was already epsilon 2, 1, 1. This difference between the average numbers on the ground level and the next excited level was disproportional to the amount of particles in the system. So it is not small changes in the occupation number, but extremely great changes. And this is why all our calculation was simply erroneous. We also managed, by using this condition that our hypergeometric function of fugacity can only reach this level of 2.612, we found out that our critical temperature for helium is around 3 Kelvin. So what exactly happens when we approach this temperature? Okay. Let us plot it. So if we plot N0 average as a function of the temperature, what do we expect to see? We expect that when the temperature is extremely high, the amount of particles for any given level is not a macroscopic quantity. It can be big, but it's not a macroscopic quantity. So if I have on total in the system, on average, around 10 to the power 22 particles, the numbers of particles that are occupying the ground state level is not large, it's small. Small can be a big number, but it's small compared to 10 to the power 22. Okay, so if we divide it by the total number of particles, what we see is that for high enough temperatures, this number is very, very close to 0. Now, at some point, we're reaching this critical temperature. Okay? The moment we are reaching this critical temperature, all calculations that we previously have performed are simply wrong. Why they're wrong? We expect that there should be some sort of a discontinuity, okay, in the behavior of the average number of particles for the lowest level. What this actually means, this means that if we will continue to decrease our temperature, N0 divided by N, it can be small, but it's going to be, okay, of the same order. Eventually, we expect that for 0, there should be all the particles, sorry, this is bad, all the particles will sit exactly at the possible lowest possible energetic level. Okay? So we expect to see something that will look like this. Okay? We are not completely sure what happens in this region. Okay? So this is a phase transition because we had a behavior that had almost 0 number of particles at the ground level, and then we have huge number of particles at the ground level. Okay? Now this transition from 0 to something which is non-zero we will discuss later today, but it's usually called a phase transition, and this is a phase transition. We'll see over exactly what is the order of this phase transition. Why we call it a phase transition? Okay, what exactly happens? We already described it. Okay, so if we plot the energies, okay, this is our epsilon, and this is the number of particles. What happens is if we start from 0 and the next level is 1, this behavior is basically saying the following thing. When your temperature is low enough, you will have a huge pile of particles sitting in the possible lowest level. Okay? They're almost there. Almost everybody are there. Sorry. Almost everybody is there, and from time to time you will have maybe one or very small amount of particles at the excited state. Okay? What happens from the quantum perspective? What happens is all the system is occupying exactly the same energetic level. They're exactly at the same state, and they are all described by the by the same wave function. Okay? The application of this are great. Okay? When all those particles are trying to flow through the system, okay, or to move around, they are almost not spending any energy. Why? What is spending of energy? For example, electrons that are flowing through a metal. When an electron flows through a metal from classical perspective, okay, it is scattered by the atoms around it. When it scatters, it can change the energy, its own energy, and it can contribute its own energy to the surrounding, which contributes to the heat of the conductor, right? And this is why when you flow a current through a metal conductor, it's going to heat up. because all the electrons are contributing energy to the environment. When all the electrons or all our particles, okay, are exactly at the same state, in order for them to contribute, get energy from the environment or contribute energy to the environment, they have to overcome some specific gap. What is this gap? The gap between the ground state and the next excited state. When they're all sitting in the lowest possible level, they simply won't do it as long as this energy that they are expected to get from the environment or to give to the environment is smaller than delta. Okay? So this is a purely quantum effect. Now, because of that, they are not going to contribute any energy or get any energy from the environment. What exactly happens? If we are looking on a current of particles, of bosons, okay? If you're looking on a current of bosons, there won't be any friction. There won't be any scattering of energy. There won't be any heating up. Okay? So this effect calls for helium. It is called superfluidity. For electrons, we can combine several electrons to actually make up what is called Cooper pairs, two pairs of electrons. Now one will have a spin 1/2, the other one will have spin -1/2. When you combine them together somehow, they will on total have spin 0. So there it's a boson. Okay? And then they also can come to this Bose state, and then they will flow through conductor without contributing to resistance. It's basically meaning that the flow of such particles is happening when no resistance is occurring. They're not getting any energy from the outside. They're not contributing any energy to the environment, and there is no resistance. So one can say that superfluidity and superconductivity are pure effect of Bose condensation. And they occur because the preferable state is the ground state, and unlike the fermions that pile up on top of each other in the energies, all the particles are sitting exactly at the same energetic state, energetic level, okay? And there is a gap from the ground state to the next level, and it's hard to excite them. Okay? So this is effect, and it can actually, you probably see it in your lab experiments in third years, or well, you will see them later or learn about them in the condensed matters class. For us, we see that it occurs simply because of what? Of how we calculate the preferable state using the grand canonical ensemble. Okay? And there is a huge difference between bosons and fermions. Now, if we're going back to what actually happens over here, okay, we can use our theory that we developed so far in order to predict the behavior near this point. Okay? So this point is interesting. Okay? This point. We're approaching critical temperature. Okay? What happens below the critical temperature? We know, or at least we expect from our previous calculations, that the average number of particles for this state is going to be huge. Okay? Let's see what is exactly this huge number of particles. All right, so first of all, if we are not using our continuous approximation, okay, how we can calculate the average number of particles? So we can say, well, the only problem that we had is only with one single level. What is this level? The zero level. Okay? But we can always write the average number of particles that is coming from the zero level, the zero energetic level, plus the average number of particles at the excited levels. Right? Now, this guy, Green is bad, I think. This guy equals to 1 divided by e to the power beta epsilon 1, 1, 1 minus mu minus 1. Okay? The problem with actually displaying this part with this function, first of all, it's exact, but the problem is that we do not exactly what mu is. Okay? Now, on the other hand, this guy, okay, we can say, well, remember all the calculations that we previously performed? Now, we assume that there is a continuous behavior of the number of the occupation number and the distances between the different energetic levels. All the excited states, they were absolutely fine. So this delta function behavior was appearing only for the 0 state. So our previous expression that we had for the average number of particles is exact for all the excited states. Why? Because something weird is only happening for the ground state. All the other energetic levels were absolutely fine. So we can write down our expression that we had previously for all the excited states. It is simply GV divided by lambda 3 T F3 over 2 of the fugacity. Okay. So this term came from the fact that we are now explicitly using what is the average number of particles at the ground state. This term is coming from our continuous approximation for the behavior of the occupation fractions for all the excited levels. Nothing weird was happening at the excited level, so this is exactly our previous result. Okay? The only difference is that we have now this contribution, and it's a little bit weird because we don't really know what mu is as a function of t. All right, so how we still can contribute or compute the behavior of what? Of n0. Now, n excited is this function. Let's write it down. N excited is GV divided by lambda thermal 3 F3 of 2 the fugacity. Now this is true, okay, the average number of particles at the excited state. This is true for all temperatures, specifically for temperatures that are lower than our critical temperature. Now we know that average n, okay, average n is equals to GV divided by lambda Tc 3 F3 over 2 of the fugacity. At what temperature? Exactly when the temperature is equal to the critical temperature. This is what's happening. If you're looking on this point, okay, when temperature is equal to the critical temperature, our theory that we developed, that we worked so hard in order to develop this continuous approximation, works pretty fine. Okay? So we know that exactly at this point, this general expression that we have previously is fine, including the occupation fraction of the ground state. Okay? So we can compute NE, the fraction of NE by N. Okay? What it is exactly? It is GV divided by lambda T to the third F3 over 2 of the fugacity divided by GV lambda Tc to the third power F3 over 2 of the fugacity. Okay? Now, well, I'm sorry, I made a mistake over here. What should be here exactly at t equals Tc? So what fugacity equals in our calculations at the critical temperature? The fugacity was exactly 1. Okay, this is the critical behavior of this hypergeometric function. So this is 1. Okay, this is exactly 1. So we have g over v lambda t. Here we have 1. Okay. Now, we do not want to compute NE divided by N. What we want to compute? We want to compute the average number of particles at the ground state. Okay. What it is the average number of particles minus the average number of excited particles. Okay. Let's divide everything by the average number of particles. And we obtain that the fraction of particles that are occupying the ground state, it is 1 minus the fraction of all the total particles that are sitting in all the excited states. So what we're getting that n0 divided by n equals to 1 minus lambda Tc to the third power divided by lambda t to the third power. And here we have f3 of 2 of the fugacity divided by f3 of 2 of 1. Okay. Now, what is lambda t? So I usually do not remember this. What exactly was our thermal wavelength? So the thermal land wavelength was 2 h bar squared divided by m, the mass of the particles, k Boltzmann t. Okay. This means that lambda Tc divided by lambda t to the third power equals exactly to t divided by Tc to the power 3/2. Okay. Now, there is still this problem of this fugacity. Okay? But we do know that when t goes to Tc, okay, the fugacity goes to 1, and f3 over 2 of the fugacity goes exactly to f3 over 2 over 1. Okay. What this means? This means that n0 divided by the total number of particles is approximately, as the temperature goes to the critical temperature, 1 minus t divided by Tc to the power 3/2. Okay. So if we plot this, n0 divided by the total number of particle n as the function of temperature. So we have two behaviors. We have, for the temperature that is higher than Tc, okay, we have 0. We know that this guy eventually should get all the possible particles that are in the system. So it is getting to 1. And we have some sort of a transition, but this is a very sharp transition in the vicinity of Tc, because we calculated that the behavior over here is 1 minus t divided by tc to the power 3/2. Now, this might be not so interesting because, well, we calculate exactly how the number of particles is starting to grow at the ground state, okay? But what we are going to see that appearance of those power laws near some critical points, okay, points where the behavior of the system changes drastically, is going to be very interesting. They define what we already know, a phenomenon that we call a phase transition, okay? Now, what is the phase transition over here? Everything is spreading out. There are a huge number of or small number of particles for each level, okay? And then we have one distinctive level where almost all the particles are sitting. How the system is behaving, so this is we can call Bose phase, and this is regular phase, okay? And there is a sharp transition between the two phases. Okay? And we see that there is some sort of a behavior, power law behavior, that describes, okay, the behavior of the system, that describes how the system, or how this occupation number grows near the critical temperature. One can say, well, Stas, it's not so important, but people start to see this kind of behavior near phase transitions in huge number of materials. So here, it's a very specific phase transition, okay? But if we look on the transition between water and ice, and we will measure some quantity, okay? For example, something that is called permeability or the correlation functions, we will see that there is also a behavior. There is a how far away in temperature you are from the critical point, and you will see some exponents or parallels that are dominating the behavior near the transition. It happens in ice, water, water, ice. It happens in magnetizations. It happens in all imaginable phase transition that there are. So when you're near the critical point, okay, there are some parallels that appear, and they describe exactly what happens near the phase transition. Now, one can say, well, it's a curiosity, but for physicists, appearance of a parallel, and sometimes those exponents are exactly the same for many different systems, it's a sign of some sort of universality. Okay? And this brings us to this next, our last section of this class, and this is Ising Model and phase transitions. We basically want to discuss what happens in the vicinity of a phase transition, and are those parallels that I will describe and discuss in the next 3 or 4 lectures that we have left, okay, are they universal, why we think that they're universal, and universality for physicists means, well, general laws. This is interesting. Not something extremely and very specific, but something that will happen for bosons, something will happen for water, something that will happen for current, something that will happen for people, okay? A description of general phenomena that won't be dependent on exactly in the specifics of the system, but will depend on some general laws that they are describing the physics of the problem. Okay, so our next section is phase transitions, Ising model, and magnetization. Any questions about Bose-Einstein condensation? No. Okay. Phase transitions, magnetization, an Ising model. Okay. So this example of Bose-Einstein condensation and behavior near the critical temperature is actually quite a late example. People studied phase transitions. Well, we studied phase transitions when we boil water and we see the transition from liquid to gas. When we freeze it, we see a transition from liquid to solid. Okay, something very peculiar happens over there. We already noticed when we studied thermodynamics that there is sometimes a jump, okay, a jump in what in pressure, or there can be a jump in something that we call entropy. Sometimes the transition can actually occur in a continuous fashion. We call this a second order transition. Okay? But actually phase transitions were studied from many, many perspectives for the problems that include magnetic systems. Okay? So what is a magnetic system? Basically, in 2 words. Well, you probably studied this in class on electrodynamics. But for us, a magnetic system, okay, we have atoms, we have electrons, okay, and we know that the energy of a system when an external magnetic field is applied is minus m dot h. Okay, what is m? Magnetization. What is h? External magnetic field. Okay. What is the interesting phenomena over there? Well, there are systems, or what is our understanding? What is this magnetization? Where it's coming from? It's coming from some sort of internal currents, okay, that there are inside our media. Okay. We know sometimes that there are currents are contributed by free electrons or atoms. Okay, and now we understand that eventually this magnetization M, okay, it is a contribution of what? We know that it's actually mainly constructed from the spins of all the different free electrons or free particles that are inside the system. Okay, so the internal magnetization, okay, is approximately the Bohr magneton, okay, and the spin of the particle, okay, and we sum up over all the different particles that we have inside our system. Okay. So we have an electron there. The electron has a given spin. The spin has a direction. It points over there. So it contributes a specific part to the total magnetization. Sometimes we have an additional spin. Well, the system is a little bit disordered, and it points to the other direction. Okay, so, and we have to sum up over all the different directions of all the different free particles. Okay, and this produces the magnetization of a system, right? Then, then we apply an external field, okay, and this contributes somehow to the energy, total energy of the system. Now, there is a quite nice phenomena that states the following. When you heat up the system and you start to apply external field, okay, and you're going from high fields to lower and lower and lower and lower fields, and you measure the magnetization of your system. M, okay, what is M? Is this guy. The total magnetization of your system, okay, as a function of temperature. Okay. Now, when you apply the field, all right, you apply the field, there is an interaction between the magnetic field and the free particles, and because the energy is lowered if you are pointing out in the direction of the applied field, so all the different spins of all the different particles try to be in the direction of the external field, right? So we do know that when we have H that is larger than 0, we have a non-zero magnetization inside our system. Why? Because they try to be parallel to the external field, okay? As you decrease your external field, this magnetization for high temperatures is eventually going to 0. Okay? And this is something that you can see in experiments. Okay? H equals exactly to 0. Why it should be exactly equal to 0? Because what we know that magnetization is the different directions of the different spins. Now the system is somehow disordered, right, when the temperature is high enough. Okay, so we can have one spin that's pointing out over there. Okay, and due to symmetry, why won't we have also particle that is pointing out to the absolutely the opposite direction? They will cancel each other, and eventually we won't have any magnetization in the system. And this is exactly what you see for all possible, okay, things in nature. As for high enough temperatures, when you do not apply any external field and you heat up the system sufficiently, okay, you will start to see that the total magnetization of the system is 0 because everything becomes disordered. Okay, now disordered not in the sense that we described as Shannon disorder, disordered in the sense messy. Okay, at all mess. All right, now this behavior, when you do not have an external magnetic field and your total magnetization is 0, is called paramagnetic. Paramagnetic. Okay, so paramagnetic behavior, your system is disordered, all the different spins are canceling each other, the total magnetization is 0. The nice thing happens is when you start to cool down everything. Okay? So you cool the system, and your magnetization still stays 0. And then you reach a specific temperature, which we was named Tc. Now C is here not critical, but Tc, C for Curie. Okay? T Curie. And what happens exactly at T Curie? Your magnetization as the total occupation for the bosons it suddenly starts to rise up. It can be positive, okay, or it can be actually negative. We will discuss when it's positive and when it's negative, okay, but you have this surprising behavior. Okay, you lower your temperature, okay, and suddenly the total magnetization is becoming non-zero. Okay, this behavior has a name. What is the name? Ferromagnetic behavior. And the nice thing that there is a resemblance between system of bosons, this system, okay, and many other systems that behave in a very similar fashion. You change the total temperature, okay, or some other external parameter, and from a state where you had something with, you measured something, here you measured the occupation fraction, here you measured the total magnetization, it was 0, and voila, it's not 0. Why it's not 0, we don't really know, but it's interesting. Okay? And what is also interesting that the behavior near this critical point, okay, over here, this behavior, in a lot of cases was dependent on Tc minus T to some power alpha. And this power alpha was the same for many different systems. Okay? This started a huge curiosity of physicists why we will have exactly the same alpha for a magnetic system and exactly the same alpha for example transition of water to ice. Okay. It was interesting. But originally it was investigated for magnetic systems by Pierre Curie, the husband of Marie Curie. Okay. And it's quite interesting because it is completely not understood, and then they don't really know about spins, about anything. Okay? They are talking about some internal currents that are appearing in the system. Okay? They don't really understand why it's happening, and also we do not know. Well, at least we will know soon enough. But it's surprising because the assumption is the system is disordered. You have no preferred direction. You have no external field. And yet somehow there is total magnetization. Okay? Now, we term this transition order-disorder transition. So there is a distinction between the order, Shannon order and disorder, and the order and disorder over here. Why it's called an order disorder? So this is disordered phase. Disordered phase. This is ordered phase. Why order and disorder? Here, all the different spins can point out in any direction that they like. Over here, in order to create general magnetization, we need to have a big portion of particles that are pointing exactly in the same direction. Similarly to this case, in order to get non-zero occupation fraction, we need huge number of particles that are sitting exactly at the same energetic level. Here we have huge number of different particles that are pointing exactly in the same direction. Okay? We call this order because they all ordered in some specific direction. Okay? And we call it disordered because they are completely messy. So remember, there is a Shannon disorder which is related to the probabilities. Okay? And this order disorder transition which is related to the mass of the system. Okay? To actual different mass that we have inside the system. What can create such a transition? Okay. Now, if the particles are completely not interacting, like most of the system that we investigated so far, okay, there is nothing that can create a general order. Okay? One can say, look, Stas, if I look on the system as a function of time, okay, and I measure magnetization. Okay, so I'll get a piece of metal, right? I will bring it to somebody's lab because I don't have a lab, okay? And we will measure as a function of the time the magnetization. Okay, so this is a magnetization, this is time. Okay, what will happen? Okay, now this magnetization fluctuates. Why? Because sometimes, some portion of the time, this particle points over here, and then it points to the other direction, and the directions of the different spins are constantly changing. So what we will see is that there is some general fluctuations of the magnetization as a function of time. You can come to me and say, Stas, well, I measured exactly at this time over here, and I get this magnetization, which is not zero. Okay, so it's not surprising because there are fluctuations, right? There are some sort of fluctuations. At some point of time, I have a non-zero probability that some portion of the particles are pointing in a given direction. So I'll have this order that you're describing me to here. But it's not the case, okay? Because what we actually need to do, we need to average over all these fluctuations. So we need to perform what is the probability to be over here, to be over here, to be over here. And if we average over time of this signal, we will get the average magnetization is exactly zero. Okay? Can repeat this experiment many times. Okay? And I will get that on average, the magnetization is zero. So what I mean that the magnetization is zero over here is that I average it, I perform my experiment several times, I got different result each time, I average over all the different outcomes of my experiments, and I got zero for all the different times. Okay? The ordered case, okay, for the ordered case, I will get something completely different. I will get that my magnetization is fluctuating around a non-zero value. Okay? It will behave something like this. So this is disordered case. This will be an ordered case. Why? Because when I perform this averaging, okay, I will get a value which is non-zero. And this is surprising. Not actually observing a non-zero value, but observing an average non-zero value for the magnetization. This was nice, but there was also an additional phenomena that people observed when they applied external magnetic field to the system. And this phenomena is termed hysteresis. Okay? So if we have, so we plot now the magnetization as the function of the temperature. Okay? Now we can plot magnetization as a function of the external field. Now if we'll try to perform our experiment, so we're measuring magnetization, okay? We are applying external field, and we are in the disordered phase. Disordered phase. What happens when the external field is very high, okay? Also the magnetization is non-zero. As we lower our external field, our magnetization should get to 0, okay, exactly 0. And then as we lower and go on and are actually going to the negative values of the external magnetic field, also the magnetization becomes negative. Okay? Now this is nice. This is what you expect, right? We can reverse now our magnetic field. So we got to this point. We started over here, okay, and we went according to this line through 0, okay, towards some negative value. We're stopping over here and we're saying, well, now let's do this backwards. Now let's increase the magnetic field. What will happen? Okay, what you expect from a normal physical system to behave like is that, well, the magnetization only depends on the external field, okay, and then you will retreat your steps. So when you're going backwards, okay, you will just go and sit exactly on the same line. Okay? Nothing interesting is happening. The magnetization depends solely on the value of the external magnetic field. That's it. So this is the disordered phase, what is measured over here, and this is the paramagnetic phase, paramagnetic behavior. What happens at the ordered phase? Okay. So we can start from some high enough external magnetic field. Now because we have external magnetic field, the spins have a preferred direction, so there is a positive general magnetization, and then we start to lower this guy. Okay? We're starting to lower the external magnetic field. Now the general magnetization getting lower, okay? And it reaches a non-zero value. It reaches a non-zero value when the external magnetic field is 0. Okay? Okay, so we see this from this plot. Right? We are over here. When we have an external magnetic field that is 0, we should be somewhere on this plot. All right? So we should reach a non-zero value. Great. Now, if we will continue to lower to the negative values our external magnetic field, eventually all the spins are going to line up according to the external magnetic field. Okay? And we see this behavior that's going on over here. Okay? So if we start from this point, this is the direction that we are approaching. Okay. Now we are going to retreat our steps. Okay? We're starting from here and we're saying, let's increase now the external magnetic field. What is happening? So at first we're going to sit exactly at the same values that we had for going in this direction. But then they will start to separate. Okay? We will cross 0, not at the positive value, but at the negative value. Okay? And we will observe something like this. Okay? So in this direction, you do not follow the path that you took when you were going from high age to lower age. You're actually getting a completely different path for the magnetization. This is the hysteresis loop. Okay? So this is what happens for a ferromagnetic system, okay, when you're below the critical temperature, below the Curie temperature. This is ferromagnetic. Now, why it's interesting? Here we understand the behavior of the magnetization completely is defined by the external parameter, which is the magnetic field. Here, it's not only depends on the magnetic field, but it actually depends on where are you going. Or where from you're going. You're going from an ordered phase and positive magnetization, you will get one path. You're going from the negative phase, okay, you're going to get completely different path. Okay? You're saying, well, I have exactly the same external value for H. You can get two answers. You can get either positive magnetization or negative magnetization. Where we see this in this plot, we can have either this solution for low enough temperatures or that solution. Okay? This is exactly what happens when the external field is 0. You can have a positive magnetization or a negative magnetization. So those two surprising observations was the starting point of a very peculiar investigation in the field of phase transitions, statistical mechanics. Okay? And they started exactly at those two observations. We have a critical temperature, we have some sort of a dependence on history of our system, right? We have disorder and order phases, and also we start to see the same phenomena not only in the magnetic systems but in extremely large number of systems, and the mathematical behavior in the vicinity of this critical point were very, very, very similar, right? Now, the only problem with this magnetic stuff is that it's absolutely unsolvable. Okay? Why? Like most real-life problems in physics, think about what is exactly going on over here. Let's assume that we want to solve this. Okay? So we'll take a metal. Okay? We can measure everything that we want. It's easy to measure. Okay? It's not easy to be an experimentalist, but for this system, it's easy, actually not that difficult to measure magnetization and apply external field. It's not a very tough experiment, from my perspective at least, as a theoretician. Okay, but what can actually be calculated over here? Okay, so we now know the three ensembles, right? Let's start and see how we can get this behavior over here. Okay, yep.
I'm sorry, it's just like this graph, it seems as though there's some points where M could be both positive and
yes, exactly, and this is the problem. Okay, now it is, you can say, well, when the external field is negative, okay, when the external field is, or it's 0, there may be two solutions, but here I have a positive external field. All the particles should be lined up according to this field, and we see that they are not. Well, I cheat you a little bit, because if we will do this experiment, this is exactly what you will see. Now, if I will do this experiment, bring my external field to this point, and stop this shifting of the external field, I will bring H over here. I will get this magnetization and negative magnetization. I will keep the external field constant and positive, and I will start to wait. After a while, it can take day, 2, 3. After a while, this solution will start to change, and will eventually reach this point over here. Okay? So it's also time dependent. This won't happen in the paramagnetic case, but for ferromagnetic case, this will happen. So your behavior is also it also depends on the ramping. It called on the ramping of your external field. How fast you actually shifting your external field, and you actually get two solutions. Yes. Yes?
Yes, I thought about these two kinds of graphs, but I don't know the temperature for these two graphs.
So this is T above TC, and this is T below TC. And what exactly is TC depends on your structure, okay? You can look on some metallic structure, it's going to be 100 Kelvin, okay? And another structure, it can be 4 Kelvin. The TC is not universal, okay? It's exactly as the transition from water to ice depends on pressure. It depends on the structure, the critical temperature. The behavior, general behavior of the systems near the critical temperature and below and above is very universal. The exact value of the critical temperature of the Curie temperature is not universal. The behavior is universal, okay? So, well, give me an example of a magnetic system and we can look up for the exact TC, but it doesn't really matter because for any other systems the TC is going to be different. But those guys are exactly the same. And this is what's interesting. It's not that Curie found something very unique for a very unique system. He found out that he had like 10 different systems that were behaving exactly in the same fashion. He was calculating different TCs, different Curie temperatures, but all the other behavior was exactly the same. Okay. So what's the problem, in calculating this behavior? We already solved several extremely tough problems, right? We solved the Debye model, the Einstein model, the we followed the Fermi fluid, and what else? The Bose condensation. But if you think about it, okay, what is the general thing that we managed to do, okay, for all the different systems that we solved so far, right? And if you look carefully on our method of solution, we started in this system, and we eventually reached a situation where the interactions between the different particles were absolutely negligible. Okay? We always solved a system of non-interacting particles. It was the Debye system, it was the Einstein model, it was the Fermi fluid, it was the Bose fluid. Okay? So we had some sort of quantum interaction, okay? And this what gave us a very interesting behavior. But we started always with a system that was not interacting. In order to get this behavior over here, okay, we do know that if the particles are not interacting, there is not a chance that there should be order. Okay? If this particle completely does not care about what the other particle are doing, this can be in this direction, the other one have a general probability being in an absolutely other direction. We average over everybody, right? And we get no order whatsoever. Okay? In order to get this or this behavior, some sort of order must be present, and order means interactions. So for the magnetic systems, interactions are important. We have to deal with them somehow. But what this behavior actually tells us, that there, at least in the vicinity of the phase transition, the interactions somehow extremely important and they are not negligible. Okay? This is the crucial part and the crucial difference between what we have done so far and what we are going to do next. The other problem is, well, magnetic system is extremely hard system because what we need to know, what we know to do, we know how to calculate the partition function. So let's assume for simplicity that we are looking on canonical ensemble. Okay? So the partition function is e to the minus beta ei. Okay? If we know how to calculate this guy for a given system, we know the partition function, then we can obtain absolutely anything else. We can obtain the potential, we can obtain the average energy, we can obtain the average magnetization. It doesn't matter. The problem is how you calculate the partition function or how you calculate the different energetic states, right? So what we've done so far, we usually assume that all the different particles, if you're looking on quantum system, we assume that all the different particles are not interacting, and we have even more, we assume that the particles are free, right? So it was really nice to compute the different energies. The most complicated system that we have done, we assume that there are some harmonic oscillators. For harmonic oscillators, we also can assume we know exactly what are the different energies, and we can solve the system. But for real life, real physical system, you cannot do this. Okay? You don't know what the different interactions. There are magnetic interactions, electric interactions, different kind of potentials, screening effects, etc., etc., etc. It becomes extremely complicated. To solve a Schrödinger equation of n of the order of 10 to the 22 particles is simply impossible when there are interactions, and they are not negligible. And we know that they are not negligible, otherwise we are getting this solution for all the different temperatures. The moment we are getting this, we know that there are some important interactions inside the system. So one can say we are doomed. Okay? We cannot solve this. We should let the chemists run the simulations and do their chemistry, and we will do something else. We will solve one particle systems or our simple models. Okay? But this is not the way the statistical mechanics works. Okay? We see a huge problem we cannot solve. We try to model this problem by using something pretty simple, okay, solvable, but still that has this effective behavior that we observe in experiment. Okay? So in 1920, a little bit after all these observations were made, William Lenz proposed a model so it's around 1920, proposed a model that is named after his student. His name is Ising. The first name, Ernst. So Ernst Ising. Ernst Ising, which published a solution which was a wrong solution for the one-dimensional Ising model in around 1924. This model became extremely popular. So every physicist knows what an Ising model is, and you will know soon enough. This guy was a student of Lenz. People do know who Lenz is, but usually most of the credit, according to the name, goes to Ernst Ising. A little bit while afterwards, this model was solved, at least at one dimension, okay, and it gave all the results that we observed over here. So it was a transition from paramagnetic and ferromagnetic behavior. So this is 1D. Later, Lars Onsager in 1944 solved exactly this model in 2D, okay, without external field. And again, he observed this behavior from ordered to disordered. What is more important, this simple model, it's opened a field in statistical physics of how exactly to treat and describe phase transitions. Okay? And now we understand a big deal about different correlations, about interactions, how to treat interactions, etc., etc. And it all started with this simple model that tried to catch up all this magnetic behavior, but not actually solving a huge quantum problem, but proposed, well, the system, let's model the system in a very simple way and let's see what happens. This let's see what happens actually managed to focus on the essential physics and catch all this universal and general results. Nobody knows how to solve this problem even in 2D when there is external field. Nobody knows how to solve this problem in 3D. Yep. Now, a funny story about Ising. Eventually, he ended up working as an engineer. He was a Jew from Germany, and it all started in 1924. He survived the Holocaust, and it was interesting that after he was released, he suddenly discovered that his name is is extremely famous in the physicist community. but he contributed absolutely almost nothing to all this field of statistical physics. Okay, so what is the model, Ising model? We won't call it a Lenz model because the appropriate name is Ising model. It as follows. Let's look on the system. Now, our system is composed on all different particles. Okay. It can be two-dimensional system, three-dimensional system. It doesn't really matter. Now, we assume that each particle, particle number I, can have either spin +1 or a spin -1. Okay? And there are many, 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 many particles. Usually we put all those particles on the lattice. So the assumption of Lenz was, well, I have a metal. It's some sort of a crystal. I don't know exactly atoms, etc. We know it's a crystal. Okay? Now we assume that each point or each particle on this crystal can contribute spin, well, not spin at that time, but it contribute local magnetization. Okay? And there are some sort of interactions between different spins. Okay? Because this particle can have spontaneous spin either +1 or -1. The other one over here can also have +1 or -1. This is, we can call a particle J. And we need to include some sort of interactions between all the different spins that are in the system. Now, how one starts, this is equilibrium situation, how one starts to describe the system. One starts to write starts by writing the Hamiltonian or the total energy of the system. So green is bad, right? Yes, green is bad, I'm sorry. So this is +1, -1, +1, -1, and J. Okay, so what is the energy of the system? It depends on the realization on all the different spins. So we go over all the different spins that are in the system, and we say, well, first of all, there should be okay, a contribution if there is an external field. So if there is an external field, okay, H, we sum up over all the different particles from 1 to n, okay, and the contribution of each of the spins is the external magnetic field multiplied by the magnetization, self-magnetization of each of different particles. We call it spin, okay? So unusually we have some mu0 over here multiplied by SI. Now SI can be either +1 or -1. Okay. Now this is a system that of non-interacting spins. We do not expect to obtain those interesting results for non-interacting spins because, well, we assume that there should be some sort of a symmetry. Okay? Each spin can point there or in the other direction. They should cancel each other out. Okay? So we need to introduce some sort of interaction. Okay? Now this interaction comes through the coupling. Okay? How this guy works says the following. We go over all the pairs of the different spins. Okay? So we assume the interactions are two-point interactions. Okay? So the energy depends on the interaction of this guy with that guy, of this guy with that guy, of this guy with that guy. So we need to take all the different pairs of the different pairs in the system. We do not take triple interactions. They are neglected. We do not take contributions to the total energy because we have this guy interacting with this guy and with this guy, and they all somehow interact among themselves. We completely, or Lenz completely neglects this, and he says, well, how I'm going to introduce this? I'm going to multiply particle number, the spin of particle I, by the spin of the particle J. Okay? And here I will have okay, some coupling between particle number I and j. Ri minus Rj. Okay. This is coupling constant. Why Lenz invented this multiplication between the two particles? Well, he's saying, well, he knows what the result is, okay? And he says, I need a situation when I'm getting a lower energy. Remember, we need a lower energy because in equilibrium, the energy is minimal, okay? So I need a lower energy when different spins are oriented in the same direction, okay? Now, this is why I have a multiplication. I don't care if it's this direction or that direction. The only thing that I care that they will be parallel. If they are parallel and they are plus 1 and plus 1, it's a negative contribution and the energy goes down. Okay? If they are parallel and it's minus 1 and minus 1, it's again a negative contribution. Okay? And the energy goes down. If they are anti-parallel, okay, this is a positive contribution and the energy goes up. All right? So in the mind of William Lenz, he thought interaction should be such that the particle will prefer, okay, to be oriented exactly in the same direction. Okay? Now, what we are thinking over here, we're thinking that somehow what we should get, if we are, so this is the external field, this is the easy part. This part can be very important when the temperatures are very, very low, or very unimportant when the temperatures are very, very, very high. And it's absolutely non-trivial to see from this description that there should be a critical point that says when this is important or when it's not important. Now, this is what is called the Ising model. That's it. Okay? The problem is this coupling constant. Why it's a problem? Because it couples all two different pairs of particles, and they somehow, usually they have a 1/2 over here, I'm sorry. And it couples all different particles inside the system. It can depend on the distance, Ri minus Rj. It can depend on the distance between two different particles. Okay? It can happen. Sometimes it's taking to be constant. Right? But this is the starting point. The problem is this interaction term, as we will see soon enough. All right, so the moment one has an energy, the next step is to say, well, I have an energy. I have to compute the partition function. So the partition function, we assume that the number of particles is not changing as a function of time. Okay? The temperature is constant. What can change as a function of time? The energy. The energy will depend on the realization, because for some realizations, those two particles are parallel. In another realization, this particle can be +1, another particle can be in -1. We have to sum up over all different possible positions, or I'm sorry, orientations of all the different particles. Okay? So this is for a given realization, and we have to sum up over all the different Si equals S1 plus minus 1, S2 equals plus minus 1, S3 equals plus minus 1. We have to sum up over all the different possible values of all the different particles and compute this minus b of sum over I from 1 to n h mu 0 Si minus 1/2 sum over I sum over j of j Ri minus Rj Si Sj. Okay? So this is the problem Solve this for 3D and you will become extremely famous. Okay? Really. Larsen Sager, he did a lot of stuff in statistical physics. But eventually, this guy became extremely famous only for solving this guy for 2D for a very simple lattice. How one goes and tries to solve this out. So first step is to see how it's behaving when we do not have interactions. Okay? Because the first step, okay, is to solve everything when the coupling constant is 0. Okay? Because I'm trying to persuade you that the coupling constant, when it's not 0, it's a mess. We will see this. So let's at first try to see what happens when we do not have the coupling constant. By the way, does it remind to you something that you've seen before? Yes. Quiz number 2. Okay, right? This is exactly what you got, but very simplified version of the Ising model. Why I gave you the Ising model? Because it's a canonical, a very simple example of canonical ensemble. Okay, so we are starting with the non-interacting Ising model. Why? Because we can actually solve it. What we have the partition function, which is a sum S over all the different SIs of e to the power. Now we can write, we don't have this part, j of Ri minus Rj equals 0. This is the non-interacting. So we have e to the power beta sum over I h mu 0 Si. Okay? We can take h and mu 0 outside of the sum, so we have a sum over all the different Si's, e to the power beta mu 0 h sum over I Si. Now, how the sum is performed, you just start to sum up over all the different realizations. Now, you look on this and you say, if Si, S1 equals 1, I don't care what S2 is because they are not interacting. I don't care what S3 is. S2 and S3 can be whatever they like. Okay? So, I can say this, that this guy is e to the power beta mu h multiplied by 1 multiplied by a sum of Si, I greater than 1, e to the power beta mu h sum over I greater than 1 Si plus e to the power beta, this is mu 0, beta mu 0 h minus 1, okay, multiplied by sum over Si, I greater than 1, e to the power beta mu 0 h sum over I greater than 1 Si. Okay? I just looked on the values of particle 1 and I say S1 can be either 1, okay? All the different other particles can be whatever they want, or this is the second realization. I have all the realizations where the particle number 1 is minus 1 and all the other particles can be whatever they want, right? Now this term and this term are exactly the same. Okay. So I can write it down as e to the power beta mu 0 h plus e to the power minus beta mu 0 h multiplied by a sum greater than 1 e to the power beta mu 0 h sum over I this multiplied by a sum I greater than 1 e to the power beta mu 0 h, a sum over I greater than 1 over Si. Okay? Now this sum, I can say I can perform exactly the same thing with particle number 2, and with particle number 3, and with particle number 4. Okay? They are independent. This is the factorization part. Okay, so we are getting that z equals e to the power beta mu h plus e to the power minus beta mu h to the power n. Right? Because we can continue this technique for the next for the second particle, and the third particle, and the fourth particle, etc., etc., etc. Okay? This is the factorization. Our z equals to z1 to the power n, okay, when z1 is e to the power beta mu h plus e to the power minus beta mu h, and this is actually 2 hyperbolic cosine of beta mu h. Beta mu h. Right? This is the result that we obtained for our partition function. Okay? So let's write it down. Z equals to 2 hyperbolic cosine of beta mu h to the power n. Now, the moment we have this, we can calculate the average spin, right? We can calculate the different values of the spins. What is S, which is average S? I'm sorry. S is the sum over I, Si. Okay? The total spin of the system. I just sum up over all the different spins of all the different particles, and this is my total spin. Average S, okay? Average. So the average of a sum is a sum of averages, right? So S average is a sum over I, Si. Okay? Now what is Si? Si average is Z. Okay? We can, because all the different spins are not interacting, we have this factorization. Okay? So we have the following thing. We have a probability of the spin, we have a possibility of the spin to be at +1. Okay? And what is the probability of the spin to be at +1? It's e to the power beta mu h divided by z1 plus the possibility of the spin to be at the state of -1 multiplied by the probability of the spin to be at the state with -1. So it's e to the power minus beta mu h divided by z1. Okay? So what is this? It is e to the power beta mu h minus e to the power minus beta mu h, okay, divided z1 is this guy, e to the power beta mu h plus e to the power minus beta mu h. This is Si, a hyperbolic tangents of beta mu h. Okay? It is independent of I, right? Why do we know that? Because Zi is Z1. The number of the particle is completely independent. So average S is sum over I of hyperbolic tangents of beta mu h, okay, which is equals to number of particles multiplied by the hyperbolic tangents of beta mu h. Okay. Now we ask the following question. Is this a paramagnetic system or ferromagnetic system? How do we know? We look on the magnetization, right? We look on the magnetization of the total system. The magnetization, M, is a sum over I, mu 0 Si, right? Now, the average magnetization is the average values of all the different spins. It is simply mu 0 average S. Okay? Okay, so what we know, average magnetization equals to mu 0 n hyperbolic tangents of beta mu h. Okay? Now, if we plot this guy, it doesn't matter mu 0. It doesn't matter what beta is. It doesn't matter what mu 0 is. Okay? It always looks like this. So M, this is H. And goes like this. Right? When H goes to 0, the average magnetization is what? It's 0. So according to our definitions, previous definitions, this is a paramagnetic case. So the system, when all the different spins are not interacting, is paramagnetic. We do not expect to see order, we do not to see anything. Okay? We do expect to see total symmetry. Why it's total symmetry? Okay? Because as we see from here, the magnetization is 0. This means for any spin that's pointing up, there is on average another spin that's pointing down. Everything is absolutely symmetric. Our hope, or the hope of William Lenz and Ising, was that if we add this coupling term, if we add interactions, somehow they become important that we will see spontaneous symmetry breaking. What I mean by spontaneous symmetry breaking, we expect or we want to see a situation when we do not have external field and still have a preferred direction. Here it's simple, either +1 or -1, but it's still a preferred direction. Okay? Now, it's already too late today, but we see that for the non-interacting case, the system is absolutely solvable. This is a model that we can obtain the magnetization, we can calculate everything. The problem starts the moment we say J is not 0. Okay? And how to solve it we will see on Tuesday.